All right, let's get started. So, I'll upload our last homework today. So there will be like 3 or 4 problems, and you will not be able to do all of them now, but you'll be able to do them, I think, probably after next Monday. Okay. All right, so let's briefly review what we covered in our last lecture. So in our last lecture, we'll continue talking about the detection in AWGN channel. Yeah, let's review it from the beginning. So basically, this is our transmitter-receiver structure, right? And we have a noise added here, and the noise is a white Gaussian noise. And we denote R of t as the received signal. Okay, and our received structure is basically we use the received signal R of t multiply a deterministic signal f of t, and then we do an integral, right? And then we get an output signal as R, and based on R, we're going to determine whether S0 is transmitted or S1 is transmitted. Okay, and the computation is as follows. So we just compute the inner product between R of t and f of t, and we know that R of t equals to Si of t plus the noise n of t, right? And then we break this into 2 terms, right? And the result of the first term is denoted by Si. You know that this Si and Ss of t they're different, right? So this is a received continuous time signal, and this is just a number after the integral, okay? And so this inner product gives us a random noise called n here, right? And now we can characterize the distribution of capital N, right? So we assume that the mean of n of t is 0. Then we can compute the mean of capital N is also 0. And the variance of n is given by this guy, right? Yeah, I forgot this square here again. So basically, it should be sigma square, right? So the variance of the noise, and is given by n naught over 2. Remember, n naught over 2 is nothing but the power spectral density value, right? And if you do the integral of n over 2 over the spectrum, then you'll get the power of our noise, which is infinity, right? And here we assume that the norm of f of t, the norm square of f of t is 1, right? And so by some design, so this condition is very easy to satisfy, and you'll see that later, maybe in the next slide. So now we can see here, because any linear operation on the noise n of t is a Gaussian distribution, right? So then it basically means that we only need to compute the mean and the variance, and the mean is 0 and the variance is n naught over 2. Then we can say that the distribution of capital N is a Gaussian with mean 0 and the variance n naught over 2. And then we can see R is just equal to Si plus N, right? So the distribution of R is a Gaussian with mean of Si and the variance of n naught over 2 if Si of t is sent. Okay, so consider a simple example where the bipolar NRZ code is sent. So S0 of t is given by this, and S1 of t is given by this, right? And so if they satisfy this condition, S0 equals to negative S1 of t, we say that is antipodal. Okay, and so now the question is, how can we design the ft, right, our base function, right? So basically, one easy thing that we could try is that we just assume either S0 or S1 can serve as our basis function, okay? And here we assume that S0 is our basis function, and in order to make sure that the norm of ft is equal to 1, we do a normalization here, right, given by this. And when compute the norm of S0 is given by this value, a squared times t, right? And we denote that as the energy of our signal, right? Because this is the definition of the energy. Yeah, here should be from 0, not t, right? The typo. From 0 to capital T. So this is the energy of our signal. And by symmetry, we can see that the S1 norm square also equal to this value, right? Because they're just negation of each other. All right, and then we can compute the norm square is given basically the norm is given by a times square root of t, right? And then we can characterize f of t equal to basically this, right? And we can double check. The norm square of ft is basically 1, right, by some easy, simple computation. And then we can see that. So the reason it's called base function is that we can use that to represent our transmitted signal S0 and S1, right? We can see in this case, so we just need one base function, which is ft, and S0 equals to this guy, right? And S1 equal to the negative of this guy, right? And here we can double check that the norm between S0 and f of t, know that this is our receiver, right? So the norm of this is given by square root of e, and similarly the norm of S1 and ft is given by minus square root of e, right? So we know S0 and S1 now, then we can characterize the distribution of R, right? So given which one is sent. Okay, and we can see that if S0 is sent, then the distribution of R is given by this, right? And if S1 is sent, the distribution of SR is given by this, right? Both of them are Gaussian distribution, and we can sketch it, right? They look like this, right? So this is a PDF of R given S0 is sent, and this is a PDF of R given S1 is sent, right? So just Gaussian distribution with same variance but different means, like this, okay? All right, and so the example we have seen is bipolar NRZ code, right? And so that's one kind of coding or waveform we can use for transmission. And this is another example, so we call that the binary phase shift keying, or BPSK. For BPSK, so S0 is given by this, right? A quasi 2πf CT, right? So use a carrier to do that. And we times the PT here, so PT is given by this form, so duration is t, right? So this is the duration of a bit, and the magnitude of that is 1. And for S1 of t, so what we do is that we add a pi here, so that's why it's called binary phase shift keying, right? We shift the phase by pi here. Because it's just a pi, right? And then we can remove this pi by adding a negation sign here, right? Equal to negative of this guy, right? And we can see in this case, so S0 and S1 is still what? Antipodal, right? Still S0 equals to S negative of 1. And in this case, we can repeat all the computation we have before, right? By using the same definition of ft, which is given by S0 divided by the norm of F0, right? And then we can see that S0 is given by square root of t, square root of e, and S1 also given by square root of e, right? And actually, this is true for all antipodal signals, right? So the only difference is, the difference is what kind of waveform that we're using for transmission. That also determines what kind of the basis function we use for the receive, okay? And okay, so now the question is, okay, so now we know the distribution of the received signal given which one is sent, right? And how can we use this information to help us to determine which one is actually sent, right? Because we don't know that, right? So it basically means that in practice, so the distribution of this is known, but how this can help us to determine which one is sent, right? Because this one is, given this is sent, then we know the distribution, right? So we cannot want the vice versa thing, right? So given R is received, then which one is sent, right? So that is what we want. Okay, so the question is how to optimally make a decision about what was sent using R, right? So here, by optimal, we basically means that under what condition, what criterion, that the probability of error is minimized, right? Given this idea, so we design a detection approach. It's called optimal Bayesian detection. So in particular, it is a maximum a posteriori detection, or MAP, okay, rule. And this actually minimizes the probability of error, okay? So here, the posteriori basically means what we got after the measurement, right? If it's before the measurement, it's called a priori, right? And in order to minimize the probability of error, so equivalently, it is to choose the most likely I given the observation R, right? And so this basically means that, okay, so given this probability of given R is sent, given R received, then SI is sent. Okay, so basically, we want to maximize this probability in order to minimize the error, the probability of error. Okay, and then let's see how can we get this. So basically, we can basically use our Bayesian rule to write this as this divided by that, right? And then we can break it into the probability that R is received given SI is sent times the probability that SI is sent, right? The reason we need this delta here is that the probability of PR is basically 0, right? So because it's a continuous distribution, okay? So we cannot characterize the probability of exactly which R is sent. The only thing we can characterize is what is the regime of R is sent, right? So we need this small delta here. But this one can be canceled, right? If this one is canceled, then this is what we get. Okay, and this is basically our rule, but we can simplify this a little bit because the denominator FR is not a function of SI, right? So remember that the goal here is to determine which SI is sent, right, in order to maximize the probability, right? So this part is not a function of SI, then we can ignore that, right? So this will not impact our decision. And the other thing is that this probability of SI is sent is a priori probability, right? So this is given by the transmitter, right? Which is kind of hard to know, right? But we'll assume that part is known, it's given. Okay. So now the map rule becomes this one, right? We just need to find I here, where I is either 0 or 1, such that this probability is maximized, right? That's it. So this is our map rule. So now we have a few issues left, right? Given the map rule, so this rule, is here, but then how can we, make an explicit decision given this rule, right? So this is the first question that we're going to answer today. And second question is that how can we choose FT to get a better performance, or get a best performance? Okay, so now f of t is given, then, how about some other FT, right? Can we get, what's the best FT that we're going to get, right? And third question is that is this architecture optimal, or even if it is optimal, then in what sense, right? So basically in this class, we're going to answer these two questions, and for this one, then, so we're not going to answer that in our class, okay? So probably we're going to talk about that in the next class. I mean, next course, not class, okay? All right, so this is what we covered in the previous lecture. So any questions? Great. Okay, so if no question, yeah, let's continue. All right, so today, this is our lecture number 34. Okay, today we have two topics. The first one is map, or in particular, we're going to talk about ML, which means the maximum likelihood decision rule. And then, so we're going to talk about how to choose f of t, and what is the impact on different ft on our decision, okay? So yeah, now let's write down the map rule here. So that is given by the map rule is that the I hat, the estimated I, was given by arg max over I, the probability of what? R given SI sent, right? And times the probability that SI is sent, right? So this is the map decision rule, okay? Not probability, so we have this PDF here, right? Okay, and so basically, remember that for the I, we just have two choices, right? The only thing we need to do is just plug in, right? Because we know this, okay, and assume that we know this as well, right? So this is just a Gaussian distribution, right? And this is a whatever distribution, right? And then we just need to plug either I0, and then we get a number, and we just plug I equals to 1, we get another number here, and see which one is big, right? If when we plug I equals to 0 is bigger, then the decision will be 0, otherwise it will be 1, right? Just that simple. Okay, so basically, if we denote this guy as pi, right, the decision rule becomes as follows. So basically, it becomes fr given, let's assume S0, okay, and multiply P0. So if this one is bigger, then we determine S0 is sent, right? And if the other one is bigger, then we say S1 is sent, right? This notation basically means that if this is bigger, we determine that as S0, and if this one's bigger, we denote the decision would be S1, okay? So that will be our decision rule. And as we said before, so in practice, so I have no idea, the prior probability of which one is sent, right? So usually we assume, so these two are equal, okay? So basically we assume that P0 and P1 are equal, and clearly, so yeah, or we don't know that, right? If we don't know that, I think probably the most reasonable assumption is that they're equal. And in particular, in the communication system, so this makes a lot of sense, right? Because normally so the transmitted signal is after some compression, right? After some compression, so normally the probability of 0 and 1, they are equal, okay? And okay, then we'll just take these two are equal, and then the decision rule will become, so there's no P0 and P1 anymore. It will be just like this, right? Right, so this will be our decision rule. And because we don't have the a priori information anymore, so this guy is called the maximum likelihood decision rule. So this one is called the maximum likelihood, or ML, decision rule. Right, you can see because this guy is called likelihood, right? Because this guy is not probability, it's PDF, right? This is called likelihood, and basically see which one is bigger, then we're going to determine, make our decision, okay? And okay, so now let's take a look explicitly on what does this mean, right? So now I have a formula here, but what does this formula mean, right? So if we sketch it, so we kind of sketched it before, right? So what we do is that we're going to sketch the PDF of this guy and this guy, right? So basically, these two Gaussian look like this, so which is just like what we have seen before. You assume they're kind of symmetric. Okay, and now, so this is the, let's say here is square root of E, and here is, use this color, square root of minus square root of E, right? And clearly, this is FR given as 0, and this is FR given as 1, right? So this is basically, so the two PDF, right? So remember that what we do here is that when this guy is bigger than this guy, then we determine what we send is as 0, right? So what regime is, the black guy is bigger than the green guy, right? It's like after this point, right? So after this point, so every point here is bigger than the point on the green one, right? Right? And then if R is below this point, then the green one will be bigger, right? So basically, it means that, so if R is in this regime, then we're going to say we receive as 0. And if R is in this regime, and then basically we're going to see we receive a as 1, right? And basically, in this value, it's kind of like a threshold, right? Yes?
So these are both symmetric, right? They have the
Yeah.
same variance.
Yes.
opposite means.
Yes.
So does that mean they would always intersect at 0?
It's not always like that. In our case, it's a coincidence.
Yeah, because they're like, we're not using the prior, right? So they're, okay.
Yeah, exactly. There's no weight on each of these terms, right? In this case, just compare the value here, right? But it's not always the case.
Right.
But if you think it twice, I think this is a pretty good one, right? So we may want to know the middle value should be 0, okay? But anyway, so this is kind of like threshold determinant rule, right? Let's say we have a gamma, ML means gamma likelihood, right? So this is our threshold, okay? So we call that the ML decision threshold, right? Meaning that if R is bigger than this value, it's at 0. If R is less than this value, it's 1, right? Clearly, in this case, it'll be 0, right? But we're gonna characterize it explicitly, see why it is 0 in general. Okay, great. And so on graph, so this is what we mean, right? So now let's see whether we have some other meaning of it, right? Or, see maybe, yeah, now this is like a probabilistic meaning, right? Let's see whether we have some other meaning of it, right? So basically what we're going to do is that we're going to write these two explicitly and see what are the relationship between R, S0, and S1, right? See whether that makes sense or not to make this kind of decision. So basically, we say, so this guy, right, so we're going to write this out using our Gaussian distribution. So this basically equals to this, right? E to the power of half R minus. So S0 is the mean of S0 is basically square root of E, right? So we write this, and so now the mean of S0. So the mean of R in this case, right, is square root of E. Okay, and then we have a sigma here. The sigma is the same for everyone, and in particular, sigma is nothing but n0 over 2, right? We just write in this way. Okay, and for the other one, it is this guy, E minus half R plus square root of E given sigma squared, right? Okay, so now we can see that. So we can make it a bit easier, right? So basically, so this will be canceled, right? And both of them have an exponential here. So now we just need to, in order to see which one is bigger, we just need to compare this one, right? We ignore this half, right? This half doesn't matter, right? We just want to see this and this one, which one is bigger, right? So if this one is bigger, then the entire thing will be smaller. Then we're going to determine the S1. If this one is bigger, then if this one is smaller, then it will be a S0. Okay, so we just want to write it more carefully. Okay, so basically, now we have this one. Just need to compare this one, right, and this term. Okay, so now, because the negative sign here, as we said before, so we just need to reverse the sign here, right? So now this is S0, this is S1, right? If this one is smaller, then we're going to determine it's S0, and if this one is smaller, then it will be a S1, right? That makes sense? Okay, so now in this case, so this sigma doesn't matter anymore, right? Because that's a constant, so we can ignore that. Okay, so basically, in the end, so what we're comparing is this. Right? Okay, and what is that? So R minus E, square root of E, right? E is basically, square root of E is basically this value, right? And it's a scalar, so, right, if we compute this difference, normally it means what? Kind of like a distance, right? So basically, if we take a square root of it, it'll give us a distance. So we denote this guy as a distance between r and the square root of e, and the square root of e is what? This is nothing but s0, right? So basically, what does this mean? It's nothing but the Euclidean distance between r and s0. We take a square of it, and then, so it basically means that, and the other thing is the distance between r and s1, right? Okay, square. But this square doesn't matter, right? So we can basically ignore this square. Right? So we can just ignore the square. And then let's see, there's some interesting meaning of it, right? So basically it means that if the distance between r and s0 is less than the distance between r and 1, we're going to determine that is the s0 is transmitted. Otherwise, it'll be s1. That makes sense? Yes, right? So now it becomes a purely distance decision, or Euclidean distance decision, okay? So we call that, so we say this as a minimum decision, a minimum distance rule, right? So this basically means that the maximum likelihood on our AWGN channel is a minimum distance rule. Okay, and so this rule is given by this. Okay, just compare to see which one is closer, right? So if it's closer to S0, then we assume S0 is transmitted. Otherwise, S1 is transmitted. Okay. Does that make sense? Right? Therefore, it basically means that, it depends on what you receive. We don't need to compute this anymore, right? We just compare the distance. Right? See which one's closer, then we can determine which one is transmitted. Okay, and so why we can do that? I mean, those theories support us, so that's the best we can do. Okay. All right. So we have only one thing left. So which one is that? From this figure, right? So we can see it's sort of, we don't need to compute the distance between the received signal and S0 and the distance between S0 and S1, right? The only thing from this figure, the only thing we need to do is that to compare whether R is bigger than this threshold or not, right? If R is bigger than this threshold, then S0 is transmitted. Otherwise, S1 is transmitted, right? Then let's derive it, right? See whether that makes sense or not. It's almost trivial. But we can obtain that from our decision rule, from the distance decision rule, right? So basically, yeah, let's rewrite it. So if the distance, right, this is our distance rule. And in order to derive it, so it's better to make it square, right? So that's easier to compute. So let's compute that explicitly, right? So this distance basically means that r minus S0 square, this is r minus S1 square. Okay, so let's see, let's break it. So this, if we write it out, it becomes r squared minus 2r S0 plus S0 squared, right? And then it's r squared minus 2r S1 plus S1 squared. Okay, so yeah, the computation of that is pretty straightforward, right? This r squared can be canceled. And then basically we can shift this guy to one side and shift this S0 to the other side, right? So basically what we got here is that I have 2r S1 minus S0. So let's keep it S0 S1, S0 S1. Right, and then we move that on the other side, S1 squared minus S0 squared. Okay, and this guy equals to S1 plus S0 times S1 minus S0. right? And then we can see that, so this and this will be canceled, okay? And now we have a 2 here, so we move the 2 on the other side. So basically, what we get is R. Yeah, here we want to cancel that, we need to be careful, right? So we assume here S1 is bigger than 0. Right? Okay. Yeah, which is not our case. So, yeah, let me see. Okay, so on my note, I do it in a reverse way. Yeah, which is fine. Right, let's keep doing this, doesn't matter. So, yeah, let's assume S1 is less than 0. S1 is less than S0, like the same as our discussion, right? So in this case, we just need to flip the sign here, right? So basically, now it's bigger and less S0, S1, right? And then what we have here is S1 plus S0 divided by 2. Okay. So basically, that's our case, right? So let's see whether it's correct or not, right? So basically, we say if R is bigger than this, then we say it's a 0. And what is that, right? So this is exactly the same as what we're discussing here, right? So we say, okay, so if R is bigger than gamma ML, then S0 is 10, otherwise S1 is 10, right? So now we have the same decision rule here. So this guy is our threshold, the maximum likelihood threshold, right? In our case, both S1 and S0, they are negative of each other, so that will be given, it will be 0 in our case, right? But in practice, it doesn't have to be 0. So basically, the meaning of this is nothing but the average of the means of 2 distributions, right? So this is how we characterize, how we characterize the gamma, the ML threshold. Okay, that makes sense. Yeah, and I think that'll be it. So any questions? Okay, so if no question, yeah, let's continue talk about the basis. Okay, so let's summarize what we have done so far. So basically, this is our input, right? And we add some noise, right? And then our output is R of t, right? And then what we do is that we multiply ft here, right? And then we do an integral to get R, right? And then we pass R to a ML decision, ML detector. Okay, and then to get I hat or S I hat, which one is 10. Okay, so this is basically our entire communication process, right? So basically, in particular, so basically, for this part, this is the inner product, right? So this operator, so normally can be understood as a projection to some basis function, okay? And in our case, we just use one basis function, right? So this is nothing but a project onto a basis for our signal space, which is, we denote that as a capital S. So this is the dimension of our, it's not dimension, so this is our we call that, the number of element here, we call that modulation order, right? So in this case, we have S0 and S1 here. So this is our, basically, this is the space of our signal, right? So the cardinality of it, so we call that modulation order. Okay, so in our case, for the bipolar NRZ case, so this number basically equal to 2, right? So so this operator is nothing but a projection of this signal space onto a basis. Okay, so now let's see. So basically, now we need to see how can we pick f of t, right? What is the optimal way, or what is a good way to pick f of t, right? So the next question is, how can we choose f of t? Right, so I want to answer that question. Okay, so now let's see. So what are the desired properties of f of t, right? Okay, so basically f of t is a basis for our capital S, right? So in our case, it's S0 and S1. Okay, so can you think about some properties of f of t? So this is kind of a projection, right, of our signal space onto this space, right? So ideally, remember, so before we say, okay, so basically S0 of t and F1 of t, so both of them can be represented by f of t, right? Do you remember? So I think if I remember correctly, so this may equals to this times f of t. Is that right? Yeah. And this equal to minus this times f of t, right? So both of them can be represented by f of t. That makes sense, right? So basically, the first condition that we want is that, so those bases can represent all the signals exactly. But we say it's essentially exactly. Right, so this basically means that, so those functions can represent our transmitted signal in the mean square error sense. We just want to make sure the mean square error of it equals to 0. Okay, so always say that with 0 energy, 0 error energy. Right, this means in the mean square sense, right? If the mean square error is 0, then we're good. Okay, and the second property of it is that, so we don't want a lot of functions, number of functions here, right? See here, for the transmitted signal, we have 2, but we only need one basis, one function here to represent both of them, right? So we want the cardinality of the number of bases, the cardinality of the bases to be as small as possible, right? So that's desired, right? It doesn't mean we have to do that, but that would be better if we can do that. So we call that the minimal property, right? So basically, it means that we cannot achieve this 0 error energy with fewer functions, right? In this case, clearly, so this is minimal already, right? We just have one base function, right? But sometimes it may not be the case. Okay, so let's see an example. When we need more than one basis function. Okay, so consider an example like this. So let's say if it's at 0, then we'll assume that we transmit this, which is the same as before, right? It's a NRZ code. But if it's S1, then we consider something different here, right? If it's S1, so this is what we transmit, okay? A minus A here, so this is a midpoint, T half. Okay, so if this is the case, let's see. So what would be our basis function? Okay, so basically the idea is the same as before. So before what we try is that, okay, so how about we use one of them as a base? Okay, and see how it works, right? So this is what we do now. So we assume that F0, so we denote this base as F0 of T equals to this guy. Right? And so we have computed before, right? So basically, this equals to what? So equal to this, 1, T is from 0 to T, and 0 otherwise. Okay? And we know the value, when we do an inner product between S0 and F0 of T, right, which is basically given by E, right, square root of E. So now let's see what is the inner product between this and that, right? Let's see whether this can represent S1 or not, right? So let's compute it. So basically, the inner product between S1 and F0 of T, right? See what that equals to, right? So this basically, essentially is this multiplied that, right, with a different magnitude. So this will be the magnitude, and we can see, okay, so this is like piecewise integral, right? We need to use this multiply that first, and then use this multiply the second half here, right? Let's see. So we have two pieces of it. So the first integral is from 0 to T half, right? This region. And we use this multiply that, right, would be given A over square root of T dt. And then for the second half, it's from T half to T, right? And that is what? Minus A divided by square root of T dt, right? And clearly, so given the symmetry here, so this value would give us 0, right? And what does it mean? Right, so this is the definition of orthogonal. Right, so these two functions are orthogonal. Basically, it means that we cannot use F0 to represent S1 at all, right? So in other words, we basically mean, it means that, so this phase, only one base function is not sufficient to represent both of them, right? So we may need another basis function. Okay, so one reasonable thing that we can try is that we assume F1 would be nothing but this one, right? How about we use that to represent a base function, right? If we use that, clearly S1 can be represented by this, right? Okay, so we just use S1 denoted by the norm of S1, right? So we use that as another base. And then we could compute what is the inner product between S0 of T and F1 of T, right? What is that, right? So basically, this is the same as the computation here, right? So we just normalize that, right? So result will now be different in this case, right? So that will still be 0, right? So you can double check to see whether it's 0 or not, okay? So it basically means that, okay, so if this 2 is 0, it basically means that there's no way to use S1 to represent S0, okay? But with these two bases, we're fine, okay? So let's summarize what we have seen so far. So now, basically, we have to use two basis function. Okay, f0 and f1 of t. And now, let's see what is the, after, so in this case, so after the integral, so our S0 and S1, so which is a number, right? It's not a function of t. So this becomes a vector instead of scalar, right? Before it is scalar, but now we have two basis functions, right? So basically, this is the projection of S0 of t on both of them, right? So the projection of S0 on F0 of t is basically given by square root of e, right? This is what we computed before, and the projection of S0 on S1 of t is given by 0, right? Because they're orthogonal, so we just compute it right there, right? And on the other hand, for S1, so the projection of S1 on F0 is 0, and then the projection on S1 on F1 is given by square root of e. Okay, so now instead of scalar, we receive a vector. Okay, so if we use the exact same derivation of the map rule, you will see it's still a distance-based decision rule, but now when we sketch it, so we can do in this way. Right, so basically now we use a kind of two-dimensional space to represent our function space. So in this direction, we assume that is f0 of t. On this direction, we assume it's f1 of t. Okay, so now, so this guy is nothing but e. So the first is here. So this point is our S0, and this point, let's say, is square root of e, and this point is our S1. Okay, and now let's say, so when we want to make our decision, it'll still be a distance space. So basically, so this will be the distance, right? Can you tell me what is the distance? Right, here is square root of e, here is square root of e, and this one would be what? 2e, right? Okay, and now your decision rule is still like, you have to make this kind of a line, and if it's on this side, it will be S1. If it's on this side, it will be S0. Okay, but one interesting thing here to think about is, see, in this case, so S0 and S1, they are not antipodal, right? S0 does not equal to negative of S1, so this is what you got, right? So this is the distance, right? This is the distance, okay? But in the antipodal case, right? In the antipodal case, so the energy of the signal is still the same, right? The energy of the signal is E here, right? So for the anticaudal case, so if we want to write the same figure, so we just have one direction, which is f of t, right? And we have a square root of e here, and we have a negative square root of e here, right? And this is our signal S0, and this is our signal S1, right? And the distance between these two is what? 2 times square root of e, right? And this one is bigger than that, right? And intuitively, the bigger, the better, right? If they're more separate, okay? And you can see, so this is a better kind of shape compared to that, right? So in practice, So we call this figure, I mean the location, like, when we make this kind of point, we call that signal constellation. Okay? So basically in practice, once we determine what are the basis functions, then we need to determine, what are the location of the signals on the basis, to kind of optimize their distance in order to minimize the error probability, right? Okay. Yeah, I think we don't have time now. And I have another example in my notes. You can take a look, right? So basically, we have many, kind of basis function that we can use, right? So yeah, you can see. I give you another example of the basis. So this is a big part, right? So you're gonna have one problem like this in your final exam, at least. Yeah, basically I'll give you the basis and then compute the signal cancellation. Yeah. All right. Okay, I think that'll be it for today. Thank you.